How do we find local mins, local maxes, and saddle points? Well, first, how do we find critical numbers? Well, let's talk about what a critical number is. Point x comma y is a critical point of the function f of x comma y if the first partial derivatives are both 0, so f sub x evaluated at x comma y equals 0 and f sub y evaluated at x comma y equals 0, or at least one of the first partial derivatives does not exist at that point x comma y. It's usually the first thing that happens. It's usually the combination of both first partial derivatives equaling 0, though just at least one of f sub x and f sub y not existing would be technically another way to get a critical point. Yeah, it's usually the first criterion. So find both partial derivatives and set equal to 0, which sounds a lot like Calc 1, where you take the first derivative and set equal to 0. Right? So let's go ahead and practice that aspect of this first by looking at the given function f of x comma y equals x cubed plus y cubed plus 3x squared minus 3y squared plus 2, and let's find the critical points. So we will keep returning to this function even after answering this question because there's going to be some follow-up questions, right? These questions tend to be long, so it's good to reuse as much as we can. We'll first compute f sub x and f sub y. There they are. We should, by the way, both of these always exist, right? There's no square roots, there's no dividing by 0 type issues or anything like that. And so that second kind of criterion is not going to occur anyway. We just now need to see when both f sub x and f sub y are equal to 0. So let's set both equal to 0, right? So setting 3x squared plus 6x equal to 0 after factoring and all this business, I'll skip some algebra, leads to x equals 0 or x equals negative 2. Setting 3y squared minus 6y equal to 0 leads to y equals 0 or y equals 2. Recall the condition was f sub x equals 0 and f sub y equals 0. So when does a critical point occur? It's quantity x equals 0 or x equals negative 2 and y equals 0 or y equals 2. So sorry for this use of ands and ors, but the thing is, the and in the middle means that something from the first menu has to occur and something from the second menu, y equals 0 or y equals 2, has to occur. The word or, though, just means that at least one of these has to occur. Now, you can't have both x equals 0 and x equals negative 2 at the same moment. So it's like one of those from the first list and then one of those from the second list. It's like a little bit of a mix and match. You actually have 4 combinations of things. So there's 0, 0, there's 0, 2, and then there's x equals negative 2 with y equals 0, and then x equals negative 2 with y equal to 2. Those are the only possible combinations that end up satisfying this condition with ands and ors in it. If you've done a class on proofs either in a math or a CS department, or you've taken like a logic course in philosophy, hopefully this phraseology with the ands and the ors will make more sense. Apologies for all that otherwise. But here's where ask about it if you really would like to. Here's the thing: we found the 4 critical points. Right? The 4 critical points have been found for this function at the top. But now the real question is, of these 4 critical points, which ones are local mins? Which ones are local maxes? And which ones are saddle points? So in order to answer this, we're going to need 2 tools. All right. So the first thing is we're going to need this thing called the discriminant or the Hessian. So given a function f of x comma y, what we'll do is compute a new function called the discriminant or Hessian, so capital D or capital D of x comma y, and it happens to be a 2 by 2 determinant made up of second partial derivatives. So if we just apply what this determinant is going to give us, right, it's going to be upper left times lower right. So f sub xx times f sub yy minus then the cross terms here. So minus f sub xy times f sub yx. Now, furthermore, if f is continuous, which is essentially the only types of functions we're going to be ever applying this process to, then f sub xy is the same as f sub yx, right? The order of which partial derivative you do first is not going to typically matter. I mean, it does in general, but almost every function we look at is going to be continuous. So for us, we're looking at f sub xx times f sub yy minus, and then quantity f sub xy squared. Okay, so let's go back to the function we had earlier. Let's go ahead and compute the discriminant. Right, we already got these first derivatives. So if we compute the second derivative. So first of all, just f sub x, differentiate with respect to x again, you get 6x plus 6. Take f sub y, differentiate with respect to y again, you get 6y minus 6. We also need the f sub xy, which in this case is going to be the same as f sub yx. If you differentiate f sub x with respect to y, or you differentiate f sub y with respect to x, you'll just get 0. All right. And oh, sorry, this typo here. This should have been a 3y squared. Yeah, 3y squared minus 6y. So in any case, other than the typo, yeah, both of f sub xy and f sub yx should be 0. So when we set up the discriminant here, 6x plus 6, 0, 0, 6y minus 6, take the determinant there. So product and then minus product. So we get 36 times x plus 1 times x minus 1 when we kind of factor that all nice. So we will use the fact that the discriminant for this problem was 36 times quantity x plus 1 times quantity y minus 1 in just a moment.